There are rules, yeah. Okay, antiderivatives. So just to give you kind of a general idea of what you're looking at here, if I give you a function, can you calculate the derivative?
Yeah.
Okay, so f prime of x is 2x. Right? What is the antiderivative of 2x?
Oh, y squared.
X squared plus c. And we'll get to that. Okay. Yeah, so we'll get to that. But so you can see kind of the relationship between the two, right? How you know a derivative, now you already know an antiderivative. Okay? So if I ask you what the derivative of sine is,
1 over the root of 1.
derivative of sine,
Derivative of sine.
cosine, what's the antiderivative of cosine?
Negative
Sine,
sine. Oh, just sine. Plus c.
right?
Plus
Yeah,
c.
so, and we'll get to the plus c part. Okay, so if we put okay, so derivative of sine is cosine, antiderivative of cosine is sine. Okay. Yes.
C is just the constant that we
Forget the concept.
We'll get there. Kyra.
So, like, when you have that x squared, what if there's like a plus 4 added on to that? Like,
Yeah, okay.
That's the C
Yeah.
that we murdered. That's what
Does that have the same derivative?
Yeah.
It
yeah,
does.
but the topic of antiderivative.
Okay, so that's where the antiderivative, this is thank you for asking that. So the antiderivative of 2x, we are going to write it like this. It's just notation, that's all it is. This is calculate the antiderivative, okay, of 2x. We call it an integral. Okay, that's what this whole thing is called, an integral. It's very integral to calculus. Oh, they just keep coming out. So the antiderivative of 2x is
Where
x squared plus something.
Okay, so we just don't know.
Why do we have the something there?
Because you don't know if it exists or not.
Because we don't know. It could be 10, it could be 5 million, right? When you differentiate it, it drops. So if you're anti-differentiating, you got to add something there. We'll get to calculating that. It's super easy. But for now, you just put a plus c.
Okay, so that's why you have.
It's a constant.
Wait,
Yep.
you can actually calculate the constant?
Yeah, if you're given an initial value,
Huh?
like if I tell you that f at 0 is 2,
Oh.
I can calculate the value of that constant. Okay. What is the antiderivative of cosine x? Sine x? Somebody said it. Don't forget your constant. Now the constant might be 0, but we just don't know yet. Okay. You know, we're taking 3 days on this section, so baby steps. Okay. Derivative, antiderivative. So you could probably take your derivatives cards and you could probably name all of those antiderivatives now. Just because you know the derivative, you can work the antiderivative, right? And put a plus c on it. That's it. Yeah. Okay. Here is the formal definition. A function f of x is an antiderivative I've got a storage cabinet full. I'm just waiting for them to rot and then they'll make the mistake on purpose.
No. That was both amazing and
Oh, this needs to be capital F.
Why?
You'll see. That's the formal definition. Barring my writing, that capital F just gets me every time. I don't know why.
Use capital when I still lowercase
F.
Why is it capital?
Because we have to have two different functions.
Is that an arrow or?
That's an epsilon.
No, that's.
It's an E. Greek E.
Oh, I thought it was
Oh,
an
we
arrow.
use that in physics. Oh my gosh.
Yeah,
that
this
is-
means
that
X is an element of this
Yeah.
set of numbers.
Mr. Wilson's epsilon is his favorite letter.
Good.
Why don't we use like something different than F equals F?
So, thinking through this. On the last slide, okay, let's try one a little different. We had those two functions on the previous slide, right?
Yes.
Yeah.
Which one is big F of X?
2x.
Word.
2x.
Oh.
F of X is the antiderivative. Big F of X is the antiderivative. So which one?
Oh.
X squared.
Yeah, it's this here.
Big F?
Oh,
In
okay,
this
now-
definition, that's big F. Okay, this is what throws people off on this definition. Because that is F, big F prime at X, right?
Whoa.
So that's what the definition's operating under. Okay. So big F is the original little f in the case that we were thinking on the last slide. So you kind of got to keep that straight in your mind. I know it looks kind of confusing at this point, but that's how this is worded. Okay. F of X is an antiderivative. That would be the antiderivative, right? Right there. Of F of X. If F prime, big F prime, equals F of X. Okay, so a little different notation than you're used to. But that's the formal definition. You kind of have to sift through those sometimes. Okay. Fontaine, you look confused.
That hurts my brain because it says F prime X equals F of X, but what you have in the red is F, big F prime X equals little F prime X.
F prime, big F prime equals F. That's what this says.
Yeah. But it's
So
not
in the
showing.
definition, this is what it's saying. The definition of an antiderivative is considering this to be the original.
Oh, big F.
And defining it as a derivative of this function. Okay, this is not going to make a big difference for now, but that's, if you understand that, great. If not, well, whatever. Let's try another one here. Let's say the notation so if the integral of f of x equals, okay, that's another way to write what we just had on the board. It's just,
I don't know. I feel like I've
You're literally making me mad. Trust me.
draw a snake doing this. No? Okay. Means f prime of x, big F, equals f of x. Okay, that's saying the same thing as the last slide. So think about this. If I calculate the derivative of that, I get this right here, correct?
Okay.
Okay, so again, it's the same thing. You're just thinking antiderivative versus derivative. You're going the same direction.
Is big F prime of x the antiderivative?
Big F,
Prime of x.
yes.
Yes.
Okay.
Yes, sometimes I have to think it through too.
And the power rule in f of x is just the original, just plain f of x. So what the second part is saying is the antiderivative.
The derivative of the antiderivative. So here's the antiderivative, right? Calculate the derivative of the antiderivative, gives you back to the original.
Okay.
Yeah. Okay.
We're starting all over, guys.
Okay, we what do I need to do to an exponent? This is the power rule for integrals. How would I calculate the antiderivative of x to the n?
So x to the n and derivative of that is
Okay, thinking this exponent is 1. So for derivatives, we subtracted 1 and brought this down.
You add one.
Okay, so we're going to add 1.
You add one, then you add plus
X to the n plus 1. And there has to be something else there.
there's an ln x, right? There's a natural log of
Why do I need that in the denominator? Okay, so if I have the integral of x cubed,
right?
this rule says that is x to the 4th over 4 plus a constant.
Okay.
Why do I need the bottom there?
Even
Because if you had like 12x to the third, that kind of thing.
Think derivative. What's the derivative of this? 4x cubed over 4. Does that get me back to 1x cubed? It does. Right? So the derivative of x to the 4th over 4 plus c is 4x cubed over 4, which is x cubed. You can always check to make sure.
We're doing like 12x cubed.
Okay. As in the integral?
yeah.
All right, let's try it.
Oh, why?
It's 12x to what power?
4. X4.
Over,
4.
which is,
Which is 3.
Don't forget. which is the same as x to the 3x to the 4th, right?
Yeah.
So yeah, you'll just simplify it. It's a constant. You treat it the same as you do in derivatives. Now, if you calculate the derivative of that, what do you get?
12x.
Right there. Okay. So learn to think both ways, forward and backwards. Derivative and antiderivative.
I assume that integral of x to the n.
We're going to. Yeah, we'll make cards for all this stuff.
Are these ones going to be green?
They'll be a different color than what we have. What colors have we used? Orange and green.
So this one's green.
Green or yellow, I don't care.
Green.
Okay then.
So,
We're being eco-friendly today by using green paper instead of white paper.
so basically, like, we're just trying to get like bring it after when you like bring it back, like to what to not for the antiderivative.
Like check your answer.
No, when you think about back to the antiderivatives, you just take the exponent and put it underneath.
Add 1, divide by that exponent.
Okay.
Yeah. Got it?
Yeah.
You okay with that?
Yeah, I'm okay.
Okay, good. Good day. That's it for the day.
Right down your throat. Right down your throat. Put it right down your throat.
How did you go with that? No work you go off
So much fun.
Are you talking about the quotient rule for integral?
I'm super excited.
We're using a real life example.
Be sure that you don't get to that this summer.
No, that does not equal half. No, I'm not. I'm not work that one out. I'm not gonna work that one out.
If we go from 460,
Make this 1 through 4.
Okay, cool.
I'll just check and make sure that it's,
That's something we're doing.
43 and
I'm gonna do all of this. Quit it.
okay. So thinking derivatives, can you still do problems like that? Position, velocity, acceleration problems, we've used derivatives, right?
Yes.
But what if you're given velocity and asked for position?
you do antiderivative for
Antiderivative,
Oh, yeah.
right? So this would be derivative, right? What would this be? Antiderivative, antiderivative. 71 is a particle motion problem.
Oh, yeah.
Okay, so keep that in mind. All right, you have about 10 minutes. Use your time wisely because this is not a very long assignment. Cheyenne.